Ladies and gentlemen, welcome again. We are going to start the second session. This is the panel 5 about new products and services, and the moderator is going to be myself. Christophe? Allô? 1, 2. Le son, 1, 2. Ladies and gentlemen, so we are going to start the panel 5 about new products and services. If you can join in the theater, please. Thank you. So, we are going to start on a very first subject this morning, all about, let's say, artificial intelligence and trusted eyes. This very first presentation is going to be made by our platinum sponsor, Ferrocampus, and the person who is going to join us is Mr. Laurent Simon, from the Engineering High School of ENSERB in Bordeaux. Please come to the stage. 1, 2.
Hello, everybody. Thanks for the invitation. So what I would like to present you today is what kind of AI we may build for critical system like railway systems. So if you, okay. So in fact, AI, despite the fact that in the recent years, for many people, AI is exclusively machine learning systems. In fact, AI is much more broader than that. And in fact, there are two kinds of AI. They are called System 1 and System 2. System 1 is more suited to tasks where you want to think fast. So it's more related to what we call intuition for ourselves. There, in the System 1 set of problems, we traditionally use machine learning techniques. For instance, if you want to design an algorithm that make a robot walk, then you have no idea of how you walk yourself. So you cannot design an algorithm to do that by yourself. So you design a system that learns by itself how to walk. So the System 1 is more like machine learning stuff, where you want to perceive, you want to detect if this is a cat or a dog. You want to find patterns in a large amount of data. Okay? So in fact, you want to find correlations. System 2 is more like symbolic AI. So it's called old AI because it was developed in the 70s. And it's more related to when you think slowly. When you want to solve a problem like a puzzle, you need to design a strategy. And in fact, you can have some introspection of the way you are solving the problem. And this AI is more about reasoning. So you want to design a system that can think. Thinking meaning reason on some data. Okay. So System 1, you want to detect correlation, and System 2, you want to reason. This is why it's also called AI. In fact, System 2 is very important because this is where, for instance, you may find causalities in your data. Machine learning cannot find causalities. They just find correlation, and what we want to build a big AI is more to be able to find causalities between events. Okay. So here I will just show you two cases of System 2 and System 1. The first illustration is a success story of AI for railway problems. Okay. This success story is based on System 2, so it's more like reasoning. So if we want to reason, this is symbolic AI, you need to have some rule for reasoning. The rules that we will use is a very old rule that was formalized like more 2,000 years ago by Aristotle himself. It's more like you have facts, so facts are true or false. And if you know that fact A implies fact B, and you know that fact B implies fact C, then you can deduce that fact A implies C. This is very simple. Okay? It looks like a trivial reasoning system. But besides the fact that this is very trivial, very simple, this is the logic we use to prove very complex systems. Like if we want to do model verification, we want to do formal proof of complex system, this is exactly the kind of logic we are using in our tools. In propositional logic, all the rules that are on the left are written by symbols on the right. Like A implies B is written by what we call a clause, not A or B, meaning that either A must be false or B must be true. Okay, and the deduction mechanism rule is called resolution. Okay, this is just propositional logic, and so some notations. I have some technical slides just to change in your day. I mean, to make it look like more scientific presentation. So we are dealing with propositional logic formula. On the top left corner, you have such kind of formulas that we are dealing with. Like you say, x1 must be false, or x2 must be false, or x3 must be true. And you must have x3 to false, and you must have x1 to true, or x2 to true. And what kind of problem are we asking ourselves on this kind of formula? We are just trying to find a solution to this formula. A solution is just an assignment of the variables to true or false that can evaluate this logic formula to true. So for instance, if we set x1 to false, then not x1 is true. This is why it's green. And then the first line, it's a clause. The first line is true because you have at least one element that is true. The second line is true also because x3 is false. Okay, so it looks like a puzzle. I mean, you just want to find a solution to a problem. But this problem, I mean, if you can do it very efficiently, your life is in danger. Okay, this problem is one of the main problem in computer science. It's related to many other problems, and in fact, it's an archetypical problems that is hard to solve in practice. It's equivalent to attack a crypto code, okay, somehow. And so you have some notation and so on. Okay. So what kind of problem can we handle with that? And the relationship with railway problems. In fact, we can encode some problems of reachability. A reachability problem, it's with the schema on the right. So you start on the green point, and you want to check if the red point can be reachable in any number of steps. Okay, so on this problem is very simple, but of course, in practice, the kind of reachability problems we are dealing with have much more states than there are particles in the universe. Okay, so it's a little bit more complicated to check. And for instance, how can we translate such kind of problems into SAT? I'll just show you a small examples. Here, it's just an example of an additioner. Okay, you just want to add 1 to a binary encoding. Okay, so at the input of this +1 stuff, there are the bits A and B. For instance, if you send 0, 0, you will add 1, so the A will be 1. And if you have 1, 0, you add 1, then you will output 0, 1. And if you enter 0, 1, you will output 1, 1, and so on. So it's just a 1 bit additioner. Okay, A is a lower bit in the binary notation. Okay, so this is a problem. And here we just want to check if there is some state that is reachable. Okay. Okay. So in fact, this formula that I showed will encode an automaton. Okay. And the problem will be, can we start with some state, and by unrolling the automaton, can we reach something, the right state at some point? The relationship with the railways will be that you will modelize your problems, like an interlocking station, and you want to see if there is some bad states that you can reach with your protocol. Okay, so you have a protocol. This is the transition function. Okay, that say if I am in this state, then I can open the door, and I am in this state now, and so on and so on. And you want to check if something bad happens. Okay, so you can translate this transition function into propositional logic. This one bit additioner, I can encode it in a propositional logic formula. Okay, it's a little bit technical, but it's not so hard. So you say the output of A is just a negation of A, as we have seen, and the output of B is just the XOR of A and B. And for instance, in this illustration, I just want to check if the state 1, 1 is reachable from the state 0, 0. It's obvious. Okay, we have seen it in the chain, but once again, remember that we want to address problems with a number of states that is completely incredible. Okay, so how can we do that? We just unroll the transition. So we just say, okay, my first state is 0, 0. Okay, I'm starting with the state 0, 0, the initial state of my automaton. And then I say, if I start with the state 0, 0, t is a transition function, I can go to the state 1. A state 1 is designed exactly by instantiating the transition function from 0 to 1. And I do the same from 1 to 2. In fact, I unroll my automaton with the logical formula. And at the end, I just check my property. I say my byte property is 1, 1. And I say, do I have A2 and B2 at the same time, or do I have A0 and B0, or A1 and B1, meaning that can I reach the state 1, 1 after the first transition, the second transition, or the third transition? And this is what I obtain is a propositional logic. Okay, so my initial problem, my initial puzzle, can be used in this example to check the reachability of an automaton in practice. Okay, this was just the technical part of the talk. And in addition, so I'm working in the SAT field, so I'm designing SAT solvers that can solve this kind of problems. And in fact, it's amazing how fast they are. They can solve problems with millions of variables. And once again, in theory, we cannot do that. But in practice, we can do that. And they can find a solution in a space, in the search space, where the universe is very small. I mean, the search space of our solvers is amazingly much more important than the size of the universe. Okay. And why it's very important also is at the end of the computation, when the SAT solvers say, yes, you can reach the bad states, or no, you cannot reach the bad states, the SAT solver can give you a proof. The proof can be quite large. I mean, it can be like terabytes of proof, okay, of resolution steps. But you can check it with a very simple algorithm that is proved by itself. Okay, and this was a success story for railway system in the 90s. Some complicated interlocking systems were proved to be safe by this kind of approach. And we are currently trying to help, like RATP, SNCF, to prove that the design of some stations are safe. Okay, so you just want to say if the train is here and the train is here, and if I open, then there is this happen, and you don't want to have any crash at the end. And it's proved, and you have an actual proof on it. Okay. I said that I will talk a little bit about machine learning. Okay. So machine learning is something that can advise you something. So you have a big amount of data. So this is not the same approach. It's not about reasoning. You take data, you learn something about data, and then you make recommendation. So you have a big computer that worked for hours, and then the big computer says, you have to change the wheels now. Do you trust it or not? You have millions of dollars. Everybody say yes, because the performance of the computer is better than a specialist. Okay, look at this specialist. You have 90% of performance. This computer 95 is better. So, but what if instead of a computer, it's a pigeon that say change the wheels now? Why do I say that? Okay, this is an example of an experiment made a few years ago. And the problem was to detect malicious cells in medical samples. Okay, so they were giving this kind of pictures to specialists, and specialists had to rank if there is a problem or not with the image. Okay, and they designed a machine learning approach that was beating specialists. So everybody say, okay, use this instead of specialist, okay? But what was this machine learning stuff? It was pigeons. They just trained pigeons to detect if the pictures was pictures of ill person or a good, not ill person. Sorry for my English. Okay. So, yes, that's good. So the problem now is that if you have a doctor, and the doctor asks a pigeon to know if you are sick or not, can you trust it? No. But here it's exactly the same. I mean, the pigeons show much better performance than human specialists, and this is exactly the same that we have with computers now. In fact, everybody wants its ML decision system. I want to have ML to say to do something, and in fact, they are very good when it's okay to have an error. This is very important. This is the first point. The second point is that in fact you cannot trust them, because ML systems are like pigeons. I mean, they don't understand what they are doing. The doctor, when he says you are ill, you have something bad, I mean, he understands the impact for you, not the pigeons. And in fact, we need to build something special. Like artificial intelligence, we need to build artificial trust. We cannot trust in an automated system the same way we trust someone. Okay. And okay, no, I'll skip that. I'm just going for my conclusion. I'm respecting the time. So trustworthy AI is a new field. And it's very complicated because all the machine learning area, they don't care about the trust, they just care about the precision. And the precision is not sufficient. So we need a paradigm shift in the machine learning community. We need to take the trust into account. In fact, from the beginning, if we want to deploy this kind of system. So for maintenance system, in fact, system 2, so reasoning system, are used, for instance, to give you an optimal plan for putting the train into reparation stuff and so on. I mean, you have an optimal reparation plan. But System 1 are still good for detecting patterns of failures. So in fact, they are used for predictive maintenance, where in fact, if you have an error, I mean, if you just take a piece of your train and you put it in reparation, it's okay if it was not already bad. Okay, the error is okay. So the main problem in the AI community is how to take the both of the two approach, System 1 and System 2, but it's something too complicated for the next 20 years, I think. But we are working on that. Okay.
Well, thank you very
Okay.
much for your nice presentation.
Thank you.
Well, we had a very good and clear overview about artificial intelligence, machine learning, embedded systems, critical systems. Well, what can we say? Are we all pigeons or what?
Us, no, but computers, yes. Yeah.
So, can we trust computers? That's a very good transition because we are going to welcome the company Leroy Automation. Leroy Automation is, of course, a manufacturer of embedded systems, and we have the pleasure to welcome Mr. David Rambaud and Mr. Patrick Rouanet.
Okay.
So the main topic will be all about safety and cybersecurity.
Okay.
A large topic.
Thank you, Sebastian. Well, I am David Rambaud. I have been system and bit designer and manager at Leroy Automation for 6 years.
Hello, I'm Patrick Rouanet. I joined Leroy in 2006 and I work on all Leroy products, railway products.
So our department works on new products, and we also pilot feasibility studies on new technologies, and we are happy today to present some new development in relation with safety and cybersecurity. Well, some of you know our product. The Rion, the Brio, the ACS have been chosen for more than 20 years by main players of the railway market, and they represent today more than 70,000 devices installed all around the world. Our new development is a PALC for Programmable Advanced Logic Computer. It benefits of all of this knowledge that we have gained through the years, and it's also the opportunity for us to implement up-to-date technologies in relation with safety and cybersecurity. So the PALC is a modular hardware platform whose core components are a CPU module and a power supply module. And in addition, it accepts up to 10 I/O or communication modules. It accepts also a lot of redundant architecture where we can duplicate any module, including the power supply module and the CPU module according to availability and or safety objectives. It is 3U8, then it can be installed in a standard 18-inch rack, but it can also be mounted on a wall in a standalone installation. Of course, it is dedicated for railway market. It is fully compliant with 50155 standard, of course, and with all railway standards. And it has been designed to optimize maintainability, sustainability, while being cost-effective and versatile. That makes it suitable for most of ERTMS or TCMS applications, such as computing, I/O management, or gateway. Our first configuration that will be available as a prototype by June next year is a VCU. So it is composed of a CPU module and a power supply module, and a free slot available for potential extension with I/O or communication. So the CPU is based on a LS1028 from NXP, which grants a 15 lifespan, which is quite good for a modern microprocessor. It embeds sufficient memory to be comfortable with most of applications, and propose a lot of communication interfaces, such as 2 gigabit Ethernet, TSN ready, 2 next generation CAN interfaces, the CAN FD, and several serial communication also. But most important, it embeds also a secure element that opens the doors to very cool cybersecurity stuff that will be presented by Patrick. Regarding the application, we have chosen a 61131 development environment called Straton from Copadata. This is a very flexible solution that allows to develop complex applications. by maximizing the use of existing libraries, but it also allows our customers to design their own application on our hardware platforms. The next step on our roadmap is to design, of course, additional modules. So we will have digital and analog IOs module based on our patented solution already proven on the Brio. They will exist in SIL 0 and SIL 2 version, but we will also develop communication modules such as MVB or such as the next generation radio communication module. But we intend also to develop other modules that will extend the functionalities of the PALC, such as a screen or mass storage or things like that. But now let's move to the today's topics, and for that, let's have a look deep inside the architecture of the PALC.
Thank you, David.
Okay.
The PALC is divided in two modules, the CPU modules on the left and the I/O modules on the right. Safety data management is done by the modules on green on the slide, and the gateway embeds communication ports. The CPU itself is segregated into two blocks, the processor and the FPGA. They are linked by a PCI Express link to communicate. The FPGA manages all real-time communication between the CPU module and slave I/O boards. The slave I/O boards and also some communication, real-time communication on the CPU.
Okay, then what about the safety and cybersecurity?
So, there are different protocols and principles for safety and security. As said by TS 5701, the first principle that is that safety and security are different and should be treated as such. The second principle is that security environment should protect essential functions, safety functions. The third, threat and risk analysis is the main interface with safety analysis. And then you have to separate safety and security, but coordinate them effectively. As a punchline, we can say that if it's not secure, it's probably not safe. The proposed structure corresponds to these principles by protecting safety function into the FPGA by the processor. The processor embeds all cybersecurity principles. And we are compliant with the defense in depth principle, which defines that if you want to attack the FPGA, you must be able to first attack the CPU.
Okay, it's clear, but why have you chosen to implement the safety into the FPGA instead of the CPU? I guess it would have been easier in the CPU, no?
Yes, perhaps, but FPGA have several advantages. The main principle of FPGA implementation for safety is to keep away all safety stuff from the CPU. And second, we can allow better performances. The FPGA is better in terms of performances, hardware performances and verification process. And third, we take advantage of FPGA architecture to address safety particular details. Indeed, FPGA have several advantages when we need verification and validation with memory and pointer aspects which are better than in software. Concerning certification also, we have a full verification and coverage property in the FPGA. So we can have a closer look in the next slide. Here are the V-cycle for FPGA development. We started with this V-cycle in 2012 with EN50128 and a software processor. Then our first FPGA certification was made in 2016. Since then, we have made several products, all SIL 2 and all based on FPGA certification. All our products were certified by Certifair. And nowadays, we are following the latest EN 50179 compliance. And our latest protocol is safety TRDP.
So, okay, for safety, and what about the cybersecurity now?
On top of that, we have cybersecurity. So we are focused on customer needs, and in conjunction with 5 pillars of cybersecurity, we have implement some stuff on the processor, like secure communication, secure boot, secure OS environment, and so on. But we have to keep in mind that it's not enough only having this kind of protocols. We have to follow also this cycle particular to cybersecurity. And we have also to take into account the production process, which could be the weakest point in this chain. It must be noticed, but I said by the European Community Agency for Cybersecurity, where we are facing emerging supply chain attack, which counts for 66% of all attacks.
Okay, so what can we do at the production side then?
So, on production side, to achieve all cybersecurity needs, we have to properly set up the product as early as we can. This is necessary to prevent all stuff private or to be manipulated or to be disclosed. So, a complete manufacturing cycle should be followed. This is the provisioning cycle. And during this phase, we need to create a golden anchor to be used and trust. Having this good provisioning phase has additional benefits. We can protect our product and also all customers' needs, assets. Okay. Now, let's look inside cybersecurity capabilities. For cybersecurity capabilities, we are basing on the CPU embedded crypto element and also an embedded hardware security module. The two elements are paired during manufacturing so that we can trust them. We create a trust anchor. With this anchor, the PALC is able to manage secure boot and software updates securely. The HTTPS certificate is also stored during provisioning to avoid counterfeit. Of course, we are compliant with the latest protocols. And on top of that, we decided to allow cross-certification by our customer, so that we will be able to provide their own PKI and to manage their own root of trust.
Okay, good, but you know sometimes that our customer lose their administration password, and with all that stuff, is it possible to recover this lost password? I mean, in a secure way?
No, it's not possible to retrieve a lost password. We never stored password in any way, but we have a mechanism to reset customers' accounts. With this mechanism, we need, like a website, we need some information on the product, like serial number, MAC address, and we can be able to produce a specific password to be sent to the customer. With this password, the customer will be able to reset its account.
Okay, so you mean that we send a secret password to the customer by mail or something like that? Is it safe?
Yes. Yes, we trust our customers. Doing that is still secure because there is no secret stored in the product, and the password, if is stolen, only has an effect on one product. So only a single product could be affected.
Okay, so we see that the technology is here, but I guess that the process itself is important as it is for safety, just not the means, but also how we develop it.
Yes, yes, process is important, and indeed, the TS 50701 is not released yet, but it refers to a 62443 for product activities. So we are dealing with 62443 compliance certification for development process. On the next step, we will have a certification and obtain a certificate for the product, and we have in mind to prove that we can offer secure product with a proof. And moreover, according to TS 50701, a safety product must be at once at secure level 1. Another line of work is to embed cybersecurity in FPGA. Again, FPGA has several advantages against the software to embed security principles. It is most robust to software vulnerabilities and has no central memory. We have to notice that until now, there is no open source hacker tool available to attack an FPGA.
Okay, thank you. So we have seen that the VCU is ready for cybersecurity, but since it proposes also a lot of communication interfaces, we anticipate the fact that in the future it will be used not only as a main computer in a system, but also as a standalone device dedicated to cybersecurity by providing services such as network segregation, traffic analysis, or gateway for old field bus protocols that are not secure by nature. Well, that's it for us. I hope that you enjoyed the presentation. If you are interested in the park, it can be seen in the exhibition area. And of course, we will be happy to answer to all of your questions. Thank you for your attention.
Thank you.
Well, thank you, David. Thank you, Patrick. I think you can stay on the stage because this was a presentation quite interesting about a hardware platform for cyber security or cyber top domain. My first question would be, why cyber and not cyber security? Does it mean the same? Is it the same word?
Are you serious? Yeah.
Well, that's maybe one of my questions. And then after, I guess, we have many rolling stock integrators here, a part of the audience, safety experts as well. So I will invite Laurent to join us as well, because maybe the second question would be, how can we take the work from Laurent and how can we port it on this type of hardware? And then we let all our friends to ask all the questions.
Yeah, so as I said, the VCU of the park is a very versatile product. So since we have a microprocessor, I guess that it will be possible to implement any algorithm. I don't know if Laurent is interested in. I'm pretty sure that Sebastian will be able to sell you something.
Maybe after any other questions from any other questions from the group? Yeah, well, I can see your first question. If you can stay there, I will try to bring the microphone to this lady. Can you introduce yourself?
Sophie Glevarek from XBlue. Thank you for your presentation, very interesting. I just have a question about what is the next step of the SIL4. What is the complexity to reach SIL4 in this kind of architecture? You present a SIL2, but what is the level of achievement for that?
Yeah, so we have already a recognized experience for SIL2 products. Of course, SIL4 is one of our objectives. I would say medium time objective. It's not for tomorrow, but maybe the day after tomorrow. As an objective, we also want that the platform is an open platform. I mean, at hardware level also. So we would like to have the opportunity to open it to third party or partnership with companies that are already experienced in SIL4 in order to implement such a safety level in our park. But of course, it's something that we have in mind, and but it will be, I would guess, in 2 or 3 years. Okay.
Well, thank you for the detailed answer. Maybe may I ask for another questions, maybe from the audience? That's okay for you? Well, so I just would like to thank you for the presentation once again, all of you three, and as a gift and thanks for joining the ICT event 2021. Paolo is going to offer you some nice little present to remember your presentation. Well, thank you to all of you. I think we are finishing the first panel just on time for lunchtime. See you in about an hour for the final panel, panel number 6 in the afternoon. Thank you to you all.
When you're here, you'll discover this. You'll relish in this.